Bismillahirrahmanirrahim. Hi everyone, I hope you are all doing well. My name is Azmat Ali. I welcome you all in class of Elementary Number Theory by David M. Burton. Uh, in the last lecture, we have completed section 1.1. Today we are going to start new section 1.2 that is related to binomial theorem. I hope you are familiar with this topic from your school and college level. In this lecture, we will just revise this topic. So let us start from the formulas. Uh, if you focus on the word binomial, it is actually can be derived from the two words, or it is the sum of two words. First is bi. Bi means two, and second is nomial. Nomial means terms. So actually binomial theorem gives the expansion of the sum or difference of two terms. Whenever we have to expand the expansion a plus b whole power n, where a and b are real or a complex number and n is a positive integer, then this expansion is called binomial theorem. So let us start from the simple examples. You know, if a plus b whole power 1, this is simply a plus b. And if I say what is a plus b whole square, your answer is a square plus 2ab plus b square. Next, if we write the formula of a plus b whole cube, this is simply equal to a cube plus 3a square b plus 3ab square plus b cube. And last one, if we want to write the formula of a plus b whole power 4, this is equal to a4, 4 into a cube b plus 6 into a square b square plus 4ab cube plus b raised to power 4. From these four formulas, you can observe the following important things. The first one is the number of terms in each expansion is one more than the index. Index means power, exponent. In this formula, the index is 2, here index is 3, and here index is 4. So you can observe in each formula the number of terms are one more than the index. Suppose if you see in a plus b whole square, the number of terms are here 1, 2, 3. Similarly, if you see in the formula of cube, the number of terms are 4. And lastly, if you see in the formula of a plus b whole power 4, the number of terms are 5. So the number of terms in each formula is one more than the terms. The second one, if you observe, the exponent of the first term a decreased from n to 0, decreased from n to 0, while the exponent of the second term b increased from 0 to n. Here power of a, that is the first term, is 2, that is equal to the index 2. In the second term, the power of a is 1, and lastly here power of a is 0. And on the other hand, if you observe here, power of b is 0, power of b is 1, and power of b is 2. The last and the most important thing that we will discuss in this topic, these number in the power of a plus b whole square, the coefficients of a square is 1, coefficients of ab is 2, and coefficients of b square is 1. these numbers 1, 2, 1. Similarly, the coefficients of in a plus b whole cube are 1, 3, 3, 1. These coefficients are actually called the binomial coefficients. These are simply called binomial coefficients. At the initial stage, if you want to find these coefficients, you can make simple the Pascal triangle. In the Pascal triangle, the number at the border, these two and these two, are always 1. And the number in between the borders are always the sum of the numbers of the row immediately above. For example, if you want to find the coefficients of a plus b whole power 4, we can make here the Pascal triangle. So let us start. Let us make from the start here. The coefficients on a plus b whole power 1 are 1, 1. Coefficients of a plus b whole square will be, these two numbers are the border number that are always 1. The central number will be the sum of these two, that is equal to 2. Similarly, for a plus b whole cube, the border numbers are 1, 1. The central numbers are the sum of these two. This is equal to 3 and this is equal to 3. Next, this is the fourth row, and this fourth row will give us the coefficients of a plus b whole power 4. The border numbers are 1 and 1. The central numbers are the sum of the numbers in the third row. This is equal to 1 plus 3, 4, 3 plus 3, 6, 3 plus 1, 4. So you can notice that these numbers 1, 4, 6, 4, 1 are actually present in the formula of a plus b whole power 4. 1, 4, 6, 4, 1. Similarly, you can find the coefficients of all other succeeding powers. But this Pascal triangle has some drawbacks. When our n is a large number, when your n is a large number, suppose n is 20, then Pascal triangle has the following drawbacks. It will consume a sufficient time. To find the coefficients of a plus b whole power 20, we have to make a Pascal triangle that requires a large paper, sufficient time, and at the 20th row we can find the coefficients of a plus b whole power 20, and it might be possible that at that stage in the 20th row there may be some error. So that's why for a sufficient large number, Pascal triangle has some drawbacks. To overcome these problems, we use simply combination rule. What is the combination rule here? To find the coefficients, binomial coefficients, we can use the combination rule. There is no need to make the Pascal triangle here. This is simply given by the formula NCR, or you can write it as and read as, in some textbook you read as NCR, or in some textbook you read as N choose R. N choose R. This is simply given by n factorial over r factorial into n minus r factorial. For example, if I want to find the coefficients, binomial coefficients of a plus b whole power 4, the last expansion, the first coefficient will be 4c0. This is equal to 1. The last one is 4c1, that is equal to 4. You can calculate this by using calculator or also by using this formula. 4c2 this is equal to 6 simply. 4c3, this is equal to 4, and lastly 4c4, this is equal to 1. Suppose if you want to find the coefficients of a plus b whole power 10, 20, these are simply given by 20c0, that you may write it as 20c1, 20 choose 2, up to so on 20 choose 20. So these are the binomial coefficients in the expansion of a plus b whole power 10. Next I am writing the most generalized form, or actually called the binomial theorem, for journal or exponent n. The general formula of a plus b whole power n is simply given by n choose 0, a raised to power n, b raised to power 0, n choose 1, a raised to power n minus 1, b raised to power 1. The exponent of the first term, that is a, is always the difference of these two numbers, n and 1, that is n minus 1. The exponent of the second number is always the number this 1. N choose 2, an minus 2 b square, n choose 3, a raised to power n minus 3 b raised to power 3, up to so on n choose r, a raised to power n minus r, b raised to power r, and last term is n choose n, a raised to power 0, b raised to power n. So this is the general form of binomial theorem. In the summation form, you can write it as summation r is equal to 0 to n, n choose r, a raised to power n minus r, b raised to power r. If you expand this sum by putting different values of r, you can obtain simply this expansion. Next, we prove this theorem, this binomial theorem, by using mathematical induction. Okay. Next, we prove this theorem by using mathematical induction. We will show that a plus b whole power n is given by this sum. Firstly, we check the statement for n is equal to 1, for n equal to 1. If we put n is equal to 1 on the left side, this gives us simply a plus b whole power 1. And if we put n is equal to 1 in this summation, this gives us summation r equal to 0 to 1, 1 cr, a raised to power 1 minus r, and b raised to power r. Next, we expand this sum by putting r is equal to 0 here. This is simply is equal to, when you put r is equal to 0, this gives us 1 choose 0, a raised to power 1 minus 0, b raised to power 0, plus And when you put r is equal to 1 here, this gives us 1 choose 1, a raised to power 1 minus 1, b raised to power 1. This is equal to 1, a raised to power 1 minus 0, this is a, b raised to power 0, this is 1. This is simply equal to a plus b. So the statement is true for n is equal to 1. We suppose the statement is true for n is equal to k. For n equal to k. We suppose the statement is true for the number n is equal to k. It means a plus b whole power k is equal to summation r is equal to 0 to k n choose k a raised to power this is k choose r a raised to power k minus r b raised to power r. Next we show the statement is also true for n is equal to k plus 1. For n is equal to k plus 1, we have to show this statement is a plus b whole power k plus 1 equal to summation r is equal to 0 to k plus 1 choose r a raised to power k plus 1 minus r b raised to power r. This is our target to show. The statement is true for n is equal to, if the statement is true for n is equal to k plus 1, whenever this statement is true for n is equal to k, say this is 1. Consider a plus b whole power k plus 1. We can write it as a plus b into a plus b whole power k. Further, we can write it as a into a plus b whole power k plus b into a plus b whole power k. By using 1, a plus b whole power k is equal to this summation. So substituting the value of a plus b whole power k here, we have a into summation r is equal to 0 to k choose r a raised to power k minus r b raised to power r plus b into, also substituting again here the value of a plus b whole power k from 1, this is equal to summation r is equal to 0 to k kcr a raised to power k minus r b raised to power r. Multiply a inside the summation, similarly b inside the summation. We have this is equal to summation r is equal to 0 to k choose r a raised to power k minus r plus 1 b raised to power r plus summation r is equal to 0 to k, this is k choose r a raised to power k minus r b raised to power r plus 1. Suppose this is expression 2. Now we separately solve both summation one by one And lastly, we substitute the values of this summation in expression 2. Next, consider the first summation, and we break this summation only for r is equal to 0. So the first summation can be written as summation r is equal to 0 to k, k choose r, a raised to power k minus r plus 1, b raised to power r. Break this summation for just for a value of r is equal to 0. If we put r is equal to 0 here, this becomes k choose 0, a raised to power, by putting r is equal to 0 here, this gives a into k, a whole power k plus 1, and b raised to power 0 plus, and the remaining summation will start from r is equal to 1. So that can be written as r is equal to 1 to k, k choose r, a raised to power k minus r plus 1, b raised to power r. K choose 0, this is equal to 1. This is a whole power k plus 1, and the rest is same as r is equal to 1 to k choose r, a raised to power k minus r plus 1, b whole power r. Similarly, we expand the summation 2 just for r is equal to k. Next, the second summation, if we put r is equal to k here, and the last k minus 1 term, the second summation for r is equal to 0 to k minus 1, k choose r, a raised to power k minus r, b raised to power r plus 1 plus, if you put here r is equal to k in these terms, k is equal to r is equal to k, a raised to power k minus k, and b raised to power k plus 1. This is equal to r is equal to 0 to k minus 1, k choose r, a raised to power k minus r into b raised to power r plus 1. Kck, this is equal to 1, a raised to power 0, this is 1, this is last term, b raised to power k plus 1. Now to make these two sums identicals, this sum start from r is equal to 1 to k, and this start from r is equal to 0 to k minus 1. To make these two sums same, we replace r is equal to r minus 1. And this sum is simply equivalent to this new summation by replacing r is equal to r minus 1. When you replace r is equal to r minus 1 here, this gives us r minus 1 is equal to 0, so r is equal to 1 here. So the starting number is r is equal to 1, 2. The last number will be k. This is equal to k r minus 1 a raised to power k minus r plus 1. When you put here r is equal to r minus 1, this gives us k minus r plus 1. And the last one is b raised to power. When you put here r is equal to r minus 1, this is simply b raised to power r plus b raised to power k plus 1. Finally, we put the values of these two summations. In equation number 2, we have the value of the first summation is given by this, which is equal to a raised to power k plus 1 plus summation r is equal to 1 to k choose r, a raised to power k minus r plus 1, b raised to power r plus, and the value of this summation is given by this is equal to summation r is equal to 1 to k choose r minus 1, a raised to power k minus r plus 1, b raised to power r, and plus b raised to power k plus 1. Now both summations start from the same value r is equal to 1 to k. So these two, by combining these two sums, we can write a raised to power k plus 1 plus k is equal to r, summation r is equal to 1 to k. Start this summation, k choose r plus k choose r minus 1, and by taking common these two terms, these two terms are same in both summations, which is a raised to power k minus r plus 1 and b raised to power r, and the last term is b raised to power k plus 1. These are the two consecutive combinations. So this is simply equal to, the sum of these two is equal to k plus 1 choose r. So we replace this is equal to k plus 1 choose r. So this last sum is equal to a raised to power k plus 1 plus summation r is equal to 1 to k. This is equal to k plus 1 choose r, a raised to power k minus r plus 1 into b raised to power r plus bk plus 1. Lastly, if we merge or combine these two terms, a raised to power k plus 1 and b raised to power k plus 1, with this sum, we can write the last sum as r is equal to 0 to k plus 1 choose r, a raised to power k plus 1 minus r and b raised to power r. If you open this sum for r is equal to 0, you can obtain the first term a raised to power k plus 1. And if you expand this term only, this sum just for r is equal to k plus 1, you can obtain the last term, which is equal to required a plus b k plus 1. And lastly, we can write as the so the statement is true for n is equal to k plus 1 whenever the statement is true for n is equal to k. Hence, by mathematical induction, the given statement is true for every positive integer. So I hope now you have a clear understanding about binomial theorem. In the next lecture, we will discuss problems 1.2. So see you in the next lecture. Take care. Allah Hafiz.